guys. The machine learning algorithm that we are going to have a look at today is called KNN, which is an abbreviation for K nearest neighbors. Right. Right. So it's a very straightforward, simple, and intuitive kind of a machine learning algorithm that makes use of the proximity of a new data point with the rest of the data points in the data set. Right? Let's say I have a data set of time. This it uses the proximity or the distance between the new data points and the existing data points in order to arrive at a uh, conclusion as to what should be the value of this new guy. Right. So let's have a look at how the algorithm works. Okay. So this is the situation. Um, I have a data set with a lot of data points over here, which are classified into red, green, and blue colors. Okay. So a new guy comes along and he places himself over here. Okay. So my question is, how would we use KNN to classify this particular new data point? The very first thing that KNN does is the calculation of distances. Right? Calculation of distances. That is to say, it would calculate how far all of these data points are from the new data point. Right? So this distance, this distance, this distance. Right? To be honest, all the distance over here would be calculated. But what the algorithm really needs are the k nearest neighbors. Right? So this k over here is a hyperparameter that we, as the user, as the supervisor of the algorithm, specify. But how do we arrive at this value? Something that we will discuss towards the last. But for the sake of understanding, let's just say the value right now is 5. Right? So what it is going to do is it's going to identify the 5 nearest neighbors of the new data point. In this particular case, uh, let's see. Oops. Okay, I will draw that data point again. Right. This particular case, this blue one seems to be quite near. So does this one, and over here, here, and here. Right. So these, I believe, are the 5 nearest neighbors. So we have about uh, blue are 2, and the red ones are just here, 3. Okay. So these neighbors over here of the new uh, data point sit together in a democratic setup and basically vote as to what this new data point should be. And since we have more votes in favors of red, this new data point will be classified as red. As simple as that. The algorithm works in a very straightforward, direct manner and classify uh, new data points like this, just taking by votes of the nearest neighbors. Okay. So, with that being said, what are the benefits of this algorithm? Right. So, first of all, the implementation, as you would have seen, the implementation of the whole algorithm is very simple. Okay. Uh, it does not make certain assumption about the distribution or normality of the data or these kind of things. In general, the implementation of this particular algorithm is quite straightforward. You would have to, let's say, scale your data and bring them all to a comparable range of value. But apart from that, there's not a lot of pre-processing going on there. Right? Depends from case to case, but generally that is the case. And this is a very important point that there is essentially no training phase in KN. Right? That is why it is called a lazy learner. What do you mean by lazy learner is as soon as you feed it the training data, it does not like other algorithms, iterate itself over the data and formulate some weights. That is not happening over here. It just stores the training data at hand, and as and when a new data point comes in, it does this calculation again and classify the new data point. Right? So there is no training phase, which makes it a bit faster as well. It is versatile in terms that it can carry out classification and regression tasks. So classification is done the way that we discussed a while ago. And regression can be done by just taking, let's say, the average of the nearest neighbors, right? And adaptability to new data is also a very interesting point. That is, in other machine learning algorithm which goes through extensive kind of a training process, when you introduce new data or your data changes over the time, you would have to retrain your data to an extent in order for it to be valid in the valid to the new data, right? You would have to retrain it, run the whole process again, and come up with essentially a new model. But in the case of KNN over here, even if I, let's say, add in new data points at these spots over here, the KNN is just going to say that, okay, I have been just storing the training data anyways. I need not, learn anything new. So it's okay. You can keep on, adding the data or modifying the data. So that is not an issue when it comes to KNN. So non-parametric also means that again, something that I already said, that the algorithm does not make any assumption about the underlying distribution of the data. It does not require it to be a normal distribution like some other, algorithm does. Right? So these are few of the benefits of the algorithm, and with that set of benefit also comes a set of drawbacks as well. So first of all, the computational complexity, right? So the algorithm, as and when it receives new data, it has to do a lot of computation. And if your data is of a large size or large scale, this computation again becomes more expensive and more complex, right? Especially when you have a large number of features as well, right? That is to say, in this particular two-dimensional example, things are pretty straightforward. You could use the Euclidean distance, but that is what is most commonly used uh, to go ahead with the calculation. But when it comes to, let's say, 4, 5, 10, or even in real case scenarios, you will be dealing with hundreds of features. In those kind of scenarios, the calculation becomes a lot more difficult, a lot more complex. Right? So you would have to maybe use some sort of, uh, dimensionality reduction techniques to bring down the dimension of your data, to for it to be able to, carry out the computation. And memory intensive again, as I said, because it basically stores the whole training data with it and carries it around. If your training data itself is large, then it becomes quite memory intensive for the algorithm, right? And then sensitivity to outliers is also an issue when it comes to KNN. For example, if I had a set of outliers in the green uh, data points in this location, right? And if I come up with a new point that is over here, by taking the votes, it is pretty clear already that the three outliers over here are going to influence the decision and, convert the sky to green, right? So the presence of outliers is going to, uh, you know, influence the decision to a great extent. So get rid of those, and the right k value. That is a very important topic when it comes to nearest neighbor. How do you arrive at the right or ideal k value? There is no straightforward formula or anything similar to that is going to tell you that this is the k that you should be using, right? Let's try to understand what happens with the variations in your k value. Okay. Let's say I have this kind of a data distribution. I have a lot of mhm, a lot of pinpoints over here, okay, and a lot of green points. Just do this so that it becomes more intuitive. Okay. So when your k values are low, right, that is, let's say, start with k is equal to 1. In this particular case, it essentially means that look at your first nearest neighbor and take up his form, right? This is going to result in a kind of a decision boundary that is, hugging the data points very closely, right? A situation that you might know as overfitting, right? Similarly, if let's say we uh, have a ideal kind of k value, it's going to just smoothen in itself and fit the data in a more ideal manner. And if you increase the k value, it's going to smoothen out even more, and it might even result in a sort of a linear data, which is a linear decision boundary, which is not something that we desire for. So to arrive at an ideal k value and balance out the trade-off between bias and variance, you can maybe use cross validation techniques where you, let's say, compare the some sort of metric, some sort of evaluation, like could be accuracy or could be error, whatever, for different values of k, right? And let's say plot the accuracy over here. You might see that uh, with the low values of k, the accuracy of prediction is bound to be quite low, and it would increase, but at certain point of time, you would see that there is no such you know increase in the accuracy or improvement in the accuracy beyond a certain point of k. It might actually drop down, or it might not improve significantly. So you can identify that particular point and arrive at a good value of k. And also, some other school of thoughts around an ideal value of k is that it should usually be an odd value in order to avoid situations where you have a tie between the neighbors, right? Let's say if you have data point over here, you have uh, two purple guys over here and two red guys over here. It's saying that, so there's a dispute between this. There are methods to counter the situation as well, but it is usually said that an odd value of k is more preferable. It's not, again, I would emphasize that it is not always the case, right? So there are methods that you can use to deal with the ties over here, something that we will discuss later on. But all in all, to just get started with uh, the concept of KNN, I believe this should suffice. I hope this video helped, and we'll wait for more.